Right, well, I mean, they were up in the 80s and 90s.
Anybody home down there?
Yeah, somebody's down there, so.
Not low 80s, we're still mid to high 70s.
We have
The building typically has always ran 75.
Check out that email section.
No, I didn't see it.
Roy thought everybody had a 72. I went around and I showed him, I stayed there, and I took floor temperatures.
Do you think we'll be able to take those contacts and put them on the table so we can access them through
You want?
those
He
contacts?
just couldn't believe
Yeah.
that
Do
anybody.
you think we'll be able to take those and put them on the table where we can access them through different programs
So
and
he didn't want to hear
access?
it. That's why he wouldn't let me do it.
Like type in
He
a
didn't
couple of
want to
letters
see
and it'll
those
pop up.
You already know this, I'm terribly sorry.
Yeah, like autocomplete or something?
Yeah.
Yeah, it does. It does shit like that.
Because that's what I was thinking last night. That's that customer ID
much
number
better. The
has.
thing that I don't like is
Customer ID, you just touch that number and it comes up.
Yeah. It'll do that. It'll like start auto filling in.
Because that's what
Here's this Dan.
me and Victor Potato are doing.
Good.
this floor.
Dan, how you doing? Good. All right.
It's 2:30 in the afternoon. So I really can't do a decent floor job. I gotta do it the quickest thing I can, cut it out, put it over there, and so you've got 3 or 4 different styles of floor job.
All right.
Irritating.
I hope it's all in there.
Ever get a job number? Like, eat it. Matt, are you? Back row crap.
No.
That for the late to come guys, the visitors, people who don't care.
They try in Central Park, things aren't working. Everything.
Yeah, it's on.
I see your problem right now.
Yeah.
Has to stand over by the elevator.
Come on,
You're the one causing the problem, huh?
listen, everybody.
Oh,
You were my out that day. That's the problem right there, Dave.
There you go. Don't feel bad. I've been his help before too.
no.
Especially when I'm down in Elkhurst. I don't know what that silly
Still is. I go out and I said, was Andrew?
Just a tip. I've got a couple of programs that I've saved that I've got to do their classes.
From down there.
No.
Oh, okay.
Man, once a year I go down. That's when I started here.
I'm starting to save before and after.
Still a program?
Huh?
Still a program?
What program? Yeah, it's an Apple. It's built into iChat, which is like Apple's messenger. JV,
What's going on?
There you go.
catching one last train before you go, huh?
Oh, you did.
Where you going? Yeah, here you won't tell anybody.
I don't know if that's what you're doing or not, but I worked with a couple programs that I looked at.
You gonna go hang out with Bobby D? You going down to UP? Which one is it?
Where they do this?
Go hang out at Alvin?
Really? Did I tell you what Rick was doing?
I'll carry his pencil.
You did that poor old man you stood up and
No, I've been talking for a couple weeks.
My worst day I want to do it.
Huh?
He's still not happy.
Is he? I didn't know how he was since his boss was leaving, or the guy who recruited him or
He
whatever.
asked me, he says, "You work at VA?" And I said, "Well, I've been there before." He said, "What kind of work do you do?" I said, "All I do is backups."
He said, you better get there and get one done now, huh? We do have a current one, right? I just took Gotta get a good backup before, ESL starts down there. They shuttered. They started? Yeah. Then we also, we're gonna have to make a tie in the allergen, we're gonna make a tie in the allergen.
Over there. What, just your workstation or?
I don't understand the whole story. There's an ad going on. It was supposed to be PKU compatible and plugging the allergen rather than to us.
It was an old one.
It was. There you go.
More problems than won't work. Hey,
Here I am.
Here we are.
Okay. How come I didn't get no papers? I don't know.
You know it all. I liked it when Bob and Andy did this. They always brought donuts.
Really? We never got any donuts, Lane.
He's studying, huh? Nice.
Who just took some? I think, John, you missed the last pages of what you, I mean, you're half an education short.
Kevin, ready.
Well, you noticed today, Bruce was on time.
Both of them are there.
Both of them. You get there early, you get out of the range of that camera.
Rick, you have?
Rick needs his one on refrigeration.
Yeah, that's right. Stay awake, Rick.
Jason's got it.
I'll make sure you're doing it right.
Yeah. I figured it'd be at least a few hecklers today.
Did he determine is that 334, 335?
434 is what we went with.
Is this everybody went with?
334.
Yeah, put that button there, okay, and then the green button right after your
Another body there.
Use the short end of the
Okay, we can hear you down there this week, so be careful. All right, let's go. We're gonna do basic refrigeration today. And looking around, there's several of you that already know this, but oops, bear with me. We had a discussion earlier about heat, and this is kind of crucial to the refrigeration cycle, so we're going to review it again. All matter made up of molecules. It's in 3 different states, solid, liquid, or gas. Just like we've been seeing outside with all the snow here lately, all of our solid, our ice, has been changing to liquid and then changing back to solid again at night. What we're doing there is obviously we're adding and removing heat. 2 terms that we don't want to confuse is heat and temperature. Heat is quantity. How many bushel baskets of heat do I have? Temperature is the intensity of heat, something you can measure with a thermometer. So 2 completely different animals. We're talking about heat. It's measured. Most common that we use is the BTU, the British Thermal Unit, which is how much heat do you need to raise 1 pound of water 1 degree Fahrenheit. Now, when we're going back to our water, if we had a 1 pound block of ice and we were going to take it all the way up through making it steam, we'd end up with a chart that looks kind of like this, where we got temperature on the side and BTUs on the bottom. First thing we got to do, we've got this 0 degree block of ice. So the first thing we got to do is warm it up to 32 degrees. And so that's going to take 16 BTUs to get us up to 32. Now we've got a 32 degree block of ice. It's still ice, but we're at 32, which is our freezing point, or melting, depending on which way you're going. This first 16 BTUs, that's sensible heat, because we raised the temperature. Sensible heat is something you can sense. So we raised our temperature 32 degrees of sensible heat. Now we got to get that liquid to, or that solid to a liquid. So now we're adding another 144 BTUs that's going to change that ice to liquid.
You're talking about 1 pound of ice?
1 pound of ice. So after we've added our 144 BTUs, now we've got 1 pound of water. You notice our line turns horizontal here. We're adding BTUs, but we didn't add any temperature at all. This part in here, that is latent heat. We can't sense it with a thermometer, but it's definitely heat that's being added or taken away from our matter. So we added 144. Now we've got liquid at 32 degrees. If we want to get that up to our boiling point at 212, we're going to have to add another 180 BTUs. There again, 1 pound of water, 1 degree. So we got to go up 180 degrees. We got to go up 180 BTUs. So there again, our chart takes off upward because we can measure that sensible heat. Now we've got water up here at 212 degrees. It's not doing anything yet, but it's right up, gets to 212. And since if we're at sea level, that's our boiling point. When we start adding more heat to that 212 degree water, it's going to start boiling. So here again, our line goes horizontal again, and we got to add 970 BTUs to that water to get it from 212 degree water to 1 pound of steam. So as you can see, our sensible heat here was not a lot of BTUs really in the big picture, but our latent heats to get it from water to steam was a lot. And that 970 BTUs is a lot of heat to get up to a full, get it completely vaporized so we're completely into steam. This change of state is really the secret or what is going on when we're talking about a refrigeration system. I got drawn out here and I've got some pictures and graphs in there. Refrigeration, basic refrigeration systems, there's a few different styles, but most of them use this basic thing, your refrigerator, your refrigerated drinking fountain, your air conditioner. This is the normal, basic, simple refrigeration system. It uses some Freon developed by DuPont, I don't know how many years ago, long ago, that they found these refrigerants have a predictable temperature-pressure relationship. At a certain pressure, it'll have a certain boiling point. And that's what the chart on the, it's not the back because I got some heat pump stuff in there, but put in a temperature pressure chart. For purposes of our discussion, we're going to go R22 and pretend.
Condenser?
What's that?
With the dirty condenser?
That's right. Always. The cottonwoods have just let loose. Are they down there?
Yeah.
Are they alive down there?
Yeah, I don't know if they're having internet issues or.
I think they're faking it.
Are you alive?
Yeah, they're choppy, so I don't.
Kevin's still drinking his coffee, so things must be going okay. We're going to go through, we're going to figure it at R22. Doesn't really matter. The four main components of any refrigeration system is a compressor, a condenser, some kind of an expansion device, and an evaporator. We're going to start out right here. The compressor hopefully is pumping vapor. On a good day, it's pumping vapor.
If not, it's not going to pump very long.
On a bad day, it won't.
Yeah. And so it's pumping out, it's discharging. We're going to say it's at 245 pounds. Somebody look on my chart here. How many degrees is that? We are going to be
115.
about 115 degrees. Okay, now that is the boiling point of our refrigerant. Not necessarily the temperature of the refrigerant coming out of here. When that compressor is compressing that vapor, anytime you take 10 pounds of vapor and put it in a 1 pound bag, you're cramming all those molecules, you're creating a lot of friction, and it generates a lot of heat. So this thing and the heat of the mechanical piston, scroll, whatever you got, the motor and the compressor, we're adding a lot of heat to that vapor. So it's going to come off of here a lot hotter than 115 degrees. It's probably going to be, I don't know, 20, 30 degrees hotter than that. Hot enough you won't want to put your hand on it. So it comes off of there smoking hot, 245 pounds, and goes into this coil. This coil is outside on the side of your house. You know, say it's a 80-degree day, 80, 85 degree day. We're blowing air across this coil, 85-degree air across it, and we've got this Freon going through that has a boiling point of 115 degrees. What's going to happen? Any guesses?
Gonna condense.
That's right. Since our 80 degrees is colder than 115, we're going to take heat out of this refrigerant and it's going to condense back into a liquid. So by the time we get out of our coil here, hopefully we have a steady stream of liquid 22 at 245 pounds. This air come in at 80, 85 degrees, going out hotter. Because it's got to remove enough heat. It's got to remove all of this latent heat to get this from a vapor to a liquid. So all of that heat, that big chunk, has got to get carried away by the air. So we got rid of a bunch of heat. This liquid comes up to this expansion device, which is down in your basement, right before it goes into the inside coil. Expansion device, they have a lot of different varieties, and for the purpose of this discussion, we're not going to go into them a lot. Usually it's an orifice, or actually an expansion valve that actually measures what the temperature is going out, so it can exactly meter how much Freon to go through. But real common, they'll use a capillary tube, just a real fine piece of copper tube, so many feet long. Some clever engineer will decide how many feet long it needs to be to drop the pressure the amount they want. And they'll do that. So this is just think of it as a restriction. We got this 245 degree or 245 pound liquid coming into here and goes through this restriction. And as you see, we're piped back to the compressor, which is, of course, sucking as well as blowing. So we put this restriction in here. Now on this side, the blue side, we're going to be down, we're going to reduce the pressure down to like 75 pounds. So at 75 psi, what's my boiling point of my R22?
133.
Can't be.
44.
44? So this thing over here now is going to boil or condense at 44 degrees. So we got this liquid coming in all of a sudden, we get on the other side of this, it's dropped down to 75 pounds. So now its boiling point has just been dropped to 44 degrees. This is in your basement, in your furnace. You're sucking air from your living room, blowing it across this coil, and blowing it back out into your house. So say on a summer day that air coming back is 78, 80 degrees, 76, depending on how cold the wife cranks that thermostat down. You know, say it's 76 degrees coming into that coil. We got 76 degrees hitting this liquid with a boiling point of 44. What's going to happen now? It's going to boil back off, because all it needs to be is 44 degrees to boil, and we've got 75, so that's a pretty good heat source. So now this air coming across that coil adds heat to that liquid. That liquid then boils off, and when we get down to the end of the coil, hopefully we've got vapor again and no more liquid. So once again, we have taken all of this latent heat. From that refrigerant gets absorbed into that refrigerant. We just added all that heat. Now the water has takes 970 BTUs for a pound of water to change to steam. R22 is something different. I don't know how many BTU per pound it is to raise it. I didn't take the time to look it up. So don't quote me on 970, but the relationships are the same. You got to add a bunch of heat to that liquid to get it to boil off. So it is absorbing the heat out of that 76 degree air, probably going to drop it, you know, normal is like 15 to 18 degrees, that air temperature. So now we've got cold air blowing into your house. We've got this liquid coming back. It's completely boiled off, probably warmed up a few degrees, but it comes back at 75 pounds, and it's fairly cool. You know, it's no warmer than the 76 degrees blowing across it. So it comes back here pretty cool. It's probably going to be, you know, 50, 60 degrees. Enters back into the compressor where we start over. Compressor takes that cool gas, compresses it big time, pumps it back up to 245 pounds, comes out of here again. Now we've got that 245 pound with the heat that came off the compressor back into the condenser coil. Now we're back at 245 where our boiling point is 115, and the same thing's going to happen. We take it condenses back into a liquid and gives up all those BTUs, those latent heat BTUs, back to the outside air. And we just keep going in a circle. It absorbs heat indoors, absorbs that latent heat indoors, comes back, we pump it up to change the boiling point, we boil it off, or condense it outside, boil it off inside. So we're absorbing heat indoors, and we're condensing it, giving it up outside. They use the refrigerant for obvious reasons. You couldn't use water because your temperatures would be way hotter than you want to be in your living room. So the great stuff about this is you can get this pressure down to 75 pounds and it boils at 44 degrees. So we can just boil it off in your house and just absorb the heat right out. Make any sense at all to those of you who have never seen this before?
Water is work, you just have to have it, in a heck of a vacuum.
Yeah, your pressures, you'd have to get your pressures way down. There are a lot of different varieties of this basic system, different types of compressors, different types of coils. You know, in your household air conditioner, it's just a copper coil with aluminum fins, and you blow air across it, and it transfers that heat from the air to the refrigerant going through it. These can be on either side. There's water cooled, where this condenser coil is cooled by some water source, you know, like a well. You can have, they can both be water coils, where we're cooling water glycol.
It's called a chiller.
And that would be a chiller. But we're doing the same things here. They size the coils and design them around these pressures and temperatures that we ultimately want to achieve. So they can do a lot of different things. The next few pages here, we talk about heat pumps. A lot of people want to know how the heck a heat pump works. There's a pretty good diagram there. Heat pumps doing the same thing. All it is an air conditioner with a three-way valve, or I'm sorry, a four-way valve. What you do is it is piped in such a configuration that when you want it to be air conditioning like you are right here, the discharge of the compressor goes to the condenser the outside coil. Shouldn't call it the condenser anymore. It goes to the outside coil, and the inside coil stays just like this. When you want to go into heat mode, the discharge goes out to the inside coil, and it goes backwards through the system, and the inside coil becomes the condenser, and the outside coil becomes the evaporator. It's a little easier to follow on the first, which was first? I think the first one they showed as the cooling refrigeration cycle. You see coming out of the bottom of the compressor, it's a skinny little line, goes into the three-way valve, comes out of that bottom port, and goes through a water to refrigerate heat exchanger. This was a nice train diagram that I pilfered off the internet. They're showing a water coil and an air coil for the indoor coil. But we got that discharge of the compressor going through the water coil, which we got, you know, well water, cooling tower water going through it to cool it off. Comes up through the expansion valve into the indoor coil, where we add heat to it from indoors. Goes back up over the top, down into the three-way valve, four-way valve, sorry, reversing valve, and then back into the compressor. So everything is working just exactly like this. The only difference is they're showing the condenser, I'll call it, as a water coil. The next picture on the next page shows it in heating mode. In heating mode, when we come out of that compressor into the four-way valve, the reversing valve, Now we go up through the top of those 3 outlet ports, goes over to the indoor coil, through, hits the expansion valve, goes into the water coil, back through the valve and back to the compressor again. So you can see it just, we're reversing the flow of the Freon through the system. In heating and cooling it goes one direction through, and in heating it goes the other. So all we're doing is changing which is our high side coil and which is our low side coil. Advantage of that is in a normal air conditioning mode, I talked about at the beginning, this compressor adds a lot of heat to that gas going through it. Just heated compression and all the mechanical, electrical heat that's generated by the compressor gets added to that gas. When you're using this as a heat pump to heat with, that's a good thing. You know, you can use that heat. It's like extra heat you get. In the summer, when you're pumping it up, that extra heat, you don't really want it. You want the pressure, not the heat. So you end up making your coil and the fan a lot bigger on the outside to get rid of that. So heating efficiency-wise, that's what makes heat pumps attractive, is you get a heat with all that energy that you're using in the compressor. A great deal of it anyway. Heat pumps, again, there's a lot of different configurations. You can do an air-to-air. Both coils are air coils, which in this part of the country is not a real attractive option. The amount of heat that you're going to absorb on our evaporator, which is now outdoors in the winter, in 20-degree air, is not a lot. It's going to be really difficult to absorb much heat out of that air. So they lose efficiency drastically as the temperature gets colder outside. They sell them, so they're out there. They work. I don't know what they work to. Used to be long ago when they first came out, you got much below probably about 40 degrees outside, and the efficiency started dropping off really fast. You got down to 30, and it was horrible.
I have one in my house, and about 40 degrees it cuts out, and then the gas furnace takes over.
Is that okay?
Yeah,
From what I remember, I think it's at 25 degrees, the heat from a heat pump is roughly 1-to-1 with efficiency of electric heat.
Okay.
So it just doesn't make any sense to run them below 25 degrees.
Okay. Yeah, you lose it. So what they did, or what some configurations do, is ideally you can have a geothermal system, which is having a water loop goes down into the ground to use the ground as a big heat sink. Got some pictures there that I'm not real crazy about. But the gist of it is there's a couple of different varieties. One of them, you pipe your water out, and you'll drill wells down into the ground, and put a normal well casing. Take a PVC, goes down with a U-bend on the bottom and comes back up, so that pipe just goes down, you know, depending on your dirt, you know, 150 foot. LPS, Lincoln Public Schools, does the crap out of these things, and they'll have for a Oh, I think the high schools, they did, the last 2 high schools they built, they put in like, I would say it was about 200 wells out there, about 15 feet apart. Just make a big grid of them out there on the football field. And pipe those babies together like this. And the water goes out there, goes through the ground. That ground is a nice, even, hopefully 55 degrees. Often there's, depending on where the water table is, there's a lot of water down there, so it makes a pretty good heat sink. You're pumping hot or cold water out there and goes through that and comes back hopefully around 55 degrees. Say you're trying to heat with that. Heating with a 55-degree heat source is one whole lot better than trying to heat with a 30-degree or a 20-degree heat source. Your efficiency is really nice if you can, really good if you can keep that temperature up into the 50s. So that's one obvious disadvantage there is you got to drill some wells. That's fairly expensive to do that. There's another variety where you put it out in there and you can put it out into a pond. And basically you get it out just under the dirt or in a lake where it doesn't freeze. If the water freezes, you're in big trouble. But you can then
Freezes at the level where the coils are.
where the coils are.
They can freeze on top of the
The
lake.
top can freeze all at once, but you got to be deep enough to where you're not going to freeze. If you have the right geography at your house, you could do this, but that's fairly uncommon. There are this whole thing I'm talking about is a closed loop. You'll keep it in a closed loop. I have seen, I don't know if they do it anymore. Years ago, if you were in the country and you had a well, you could, has Rick's got one of those?
Yeah.
You just suck the old water out of the ground, run through your heat pump, and then dump it somewhere.
In the creek in the backyard.
Yeah, water your lawn with it, do whatever.
Yep.
And that is there again, you get to use that nice 50-some degree water coming out of the ground.
And that's the most efficient way because with the closed loop, the loop's always heating or cooling the ground.
Yeah.
Or with the open loop, it's not.
Yes. Yeah. With this, you're using that temperature once and then chucking it in water.
Does everybody understand what Rick just talked about banking the BTUs in the ground and discharging them out of the ground? Your ground temperature, if it's too, especially if the engineer sizes the loop too small,
Yeah.
you'll build up the temperature of the earth to a point where it won't accept, or you can't extract BTUs depending on the season you're in. So when you go into the winter time, actually you're taking BTUs out of the ground. When you get into the early summer, you got a great source down there, but then towards the end of the summer, you've been packing BTUs into the ground again. You're taking them out of the air and shoving them in the ground. So now it's harder and harder to pack those BTUs in there. So compared to the well field.
Yeah. And it's a crapshoot. It really is. They built 2 identical schools in Lincoln, high schools. I mean, they are absolutely identical. Well fields are identical in number. One of them in the summer, our loop temp warms up to 80 degrees. It gets hot.
One gets North Star or Southwest?
Southwest. Southwest gets hot. North Star, it's over there on a 100-degree day. It's running at 58, 59 degrees.
Must be a big difference in the soil.
Something down there, it's the water table, it's the soil. For some reason, one of them cannot get rid of that. It doesn't seem to be a problem in this, like the winter.
Through like a wave.
They got like 275 wells out there.
Do they?
There's somewhere.
Yeah.
Do you notice that that doesn't really track with outside air temperature? It's more, later in the season?
It didn't really seem to matter.
Oh, really? Tracks more with outside air temperature?
Well, it didn't look like it was really a cumulative thing, like for 2 weeks it was okay, and then the next 2 weeks, you know, or it was fine in June, but it wasn't good in August. It really didn't seem to matter. Once it got hot, and a lot of heat pumps were running, the loop temperature got out. I mean, it was probably more driven by
And then if it cools off, it catches up.
Yeah. Yeah.
Need you to.
And we tried
You're going down.
speeding up the water going through there, slowing the water down. It makes no difference. And I don't know, one of the problems is you get all those wells piped together out there, and you know, you send a pipe down under the ground, and this big pipe comes back out of the ground. Which ones of these are airlocked? You know, how do you know? When they do their grids like that, I think they have like 8 to 10 wells per loop like this. And they'll all come back into a pit where they're all tied together and come out. So it's really tough to know, you know, are they only getting good flow through half of their wells? It's just, they don't have any good way of figuring it out right now. They're looking at putting some flow sensors on each one of these laterals to see if they really got GPM going through them or not. But something's really weird between the two, and because they're vastly different, and it's identical building. They use the same drawings. They just
Same contractor?
the well contractor was the same. The piping contractors were different, but the well guys who did everything up to the building, they were the same. And they do they'll put the casing in, and then they fill it up around here with, I can't remember the name of the stuff. This is gray stuff.
Starts with B.
Yeah. That,
Yeah, that's it.
that sounds right. And they slug them with that. So,
It's a soil stabilizer.
is it?
You use to make boards to
Mm-hmm.
stabilize the hole.
Yeah. So, I don't know. It's interesting though, that it's kind of driving them crazy. The first year they thought, well, maybe we got air in it, and the next year they got more worried, and so it is odd. Other stuff, that's geothermal, and that's ideal if you can do that, because that is free. All you got to do is pump it. Other than that, it's free. If you don't have something like that, you're going to have a source of heat and a source of cool. Source of heat is usually a boiler. So you're going to have, as we're sucking heat out of that loop, we're going to have something to put heat back into that water again. And so it's usually a boiler. In the summer, when we're heating the loop, we'll have usually a fluid cooler or a cooling tower to cool it off, cool that back off again. that is, I mean, obviously you have this nice energy efficient thing going here with the heat pump, but then when you got to start paying for the heat, you know, with a boiler, heat it back up again, your efficiency starts going to hell again. I mean, you're spending a lot of money on reheating them. And at that point, I question whether the maintenance, the cost of the equipment is worth, you know, why not just heat with the boiler? If you're going to be firing a boiler to heat anyway. But anyway, that's personal opinion. So let's see what else we got. You're always going to have, on a geothermal, you're always going to have some kind of a pumping system. Hopefully, you can have the pump only run when you need it. Otherwise, you're burning kW with a pump running all the time. Down at the schools there where we have these, they think it's a great deal to be able to, oh, here's the tokens. They think it's a great deal to be able to run in the summer when there's no kids there. You know, we can run 2 classrooms if we want to, or 1 classroom. But you do got to kind of remember what the efficiency is like there, even though they're geothermal. You know, on that high school, those are like 75 horse pumps to pump that water. And so we've got a 75 horse pump cooling one classroom, plus the heat pump. So, you know, nothing's free. There's things to be considered with all of them. What did I miss? That is about it. The big thing these days is to try and make this, they haven't gone away from this basic design forever. They keep trying to make all the pieces better over and over. The compressors, they make different styles. Now, in the old days, it was always just a reciprocating compressor. Now they have scroll, they have different rotary designs. They have, for a big chiller, they'll have a centrifugal compressor. The coils, you notice your air conditioners on the outside of your house are getting bigger and bigger. That's because they want this coil to be bigger and bigger so we can get rid of that heat and use smaller fan to do it with, because we got to have that fan here blowing air. So the smaller the fan you can use, the better, the less,
The more efficient it is.
the more efficient it'd be, the less energy you burn to get rid of that heat. So bigger and bigger coils. They get better designs. What happens when all the cottonwood in the neighborhood sucks into this coil here?
Efficiency goes down a little bit.
Efficiency goes down terribly. Our pressure probably goes up. We can't get rid of the heat.
How do you keep it out of there?
Wash it.
Where you cut the trees down?
Yeah, there you go. That's the best solution. It's got
It
this.
looks like it's snowing in my neighborhood.
Yeah. Yeah. Oh, I know. I've got one. There's an enormous cottonwood at the bottom of the hill, which is like, it's almost 3 blocks away from my house. And I get a ton of cotton every year from that sucker. It finds your air conditioner. All you can do is, when you I don't know how I can draw this. Your condenser is going to have, it's going to have a fan on one side of the coil, and a lot of them suck in from the outside and the fan blows it, so it's sucking through there. What you want to do is disconnect the power. Of course, you electricians know that. And get from the inside and squirt water out, so if the cotton's getting sucked in the coil this way, hose it out from the other way to blow it out, to wash it out. All you can do is keep hosing it down and keep it clean.
Air compressors work really good too.
What?
You got an air compressor, you just blow air through it, and it'll shoot that cotton out.
Problem with any air or water that's too high a pressure, those aluminum fins can't take much, and so they can bend over on you if you get too much pressure, like a pressure washer. Even you can bend them suckers over, and then you just lost whatever you gained a minute ago.
Probably help you get a couple feet off the ground too, like on the side of your house with brackets.
Why?
Well, because everything rests on the ground more.
Those are more made for heat pumps.
Heat pumps
Keep
do
the heat
that,
pump up
yeah.
out of the snow.
Get it up out of the snow. Keep your bushes and stuff away from it. I drive by one. I drive by a house that's not too far from my house, and here's the wall, and here's the ground level, and here's the air conditioner here, which was too damn close to the house in the first place. You read the book and it'll tell you to put it like, 24 inches away from the house. This is a nice top discharge. Well, they really wanted to save energy in this house, so they added a fireplace. And but the damn air conditioner was there on the side of the house if they wanted to put the fireplace. But they could still fit it in. So they framed out like this and put their fireplace flue coming off of there. And I ain't kidding you, that top of the air conditioner to the bottom of that chimney is like 6 inches. I can't believe that sucker works at all.
Can you imagine trying to take the top of that, trying to clean it?
Yeah, yeah, it's just amazing. Keep that outside coil clean. Inside coil is the same way. It's cold, and you all know what happens to cold things. It's going to take the moisture out of the air. So whenever it's running, it's going to be wet. And you take a nice wet surface and run air across it, and dirt's going to stick to it. So no matter how good your filters are, unless you got HEPA filters on your furnace, and if you did, it wouldn't be able to blow any air because it didn't have a big enough blower. This sucker is going to get, over time, loaded up with dirt, hair, crud, lint. Those dust bunnies are going to suck out from under the bed and stick to that thing. It makes a nice mat on the inside of that A coil above your furnace. And so
Like hell trying to get to it.
they don't make them. Guy installing it, he's not coming back. He's not a service guy, so he screws that ductwork up tight and dum-dums off the refrigeration lines around it and leaves. And yeah, then you've got to get to it somehow to get in there. But it's the same thing. You block that airflow, and now we can't get heat to the coil. So what happens there is if you come out to your compressor and look, and this line out here is a big chunk of ice coming all the way back. That's because you've got liquid coming all the way back here, and it's trying to boil at 44 degrees, and it can't find any heat to boil with. So it's going to keep trying until it gets all the way back. If liquid makes it back to the compressor, those valves, that suction valve on the compressor won't last long.
How does the low ambient kit work on that? What is that?
Low ambient, what that will do is, there are several methods. The easiest of which is, we've got to keep this coil, as it gets colder and colder outside, our pressure is going to go down because because it's colder. So we have to keep that pressure up in order to push the liquid through.
In order to keep the evaporator from freezing up?
Well, to keep this 75 pounds at 75, we've got to keep our pressure up here to at least a minimum. So the easiest option is when our pressure goes down too far, turn off the fan. Or if there are multiple fans, stage them off. You can get more elaborate with there are hot gas bypass gadgets to where we're sensing the low side pressure. If that pressure drops too low, we'll pump some heat, some high pressure over from the other side. What else do we do? That's basically a low ambient, just to keep the pressure up. Just to keep it, they're designed to be somewhere in that area, and you can fluctuate a ways, but it can't keep going forever. So you have to keep it in that range.
What's the advantage of a scroll over a recent?
You know, I don't know.
Just liquid slugging.
I think it's just
with liquid slugging and a scroll as it would.
I don't
Well,
know.
no, it's that they'll handle a little bit of liquid slugging.
Yeah.
The valve, they don't have the flap reed valves.
Reed
like,
valves. Yeah.
Reciprocating compressor does.
Yeah, I don't know a lot about those. Those came around after I got out of the business.
You're still in business.
Out of the field.
Out of the field. That's all I've got on refrigeration. It's, you know, it's one of those things that's kind of weird to think about, but it's a pretty simple process, actually. The pieces, parts look different on different units, but they're really all doing the same thing. And just like every other thing we've kind of been hammering on you on through all these classes, is it's all about heat. I mean, that's 90% of what we're doing. We're moving heat around, we're transferring it. It's all about the heat. So, thank you. Good night. I saw Kevin.
Andy, get your red.
Where bodies are, you know, heads are, that type of thing. So that is a point where I always harp on engineers and owners. I like discharge air sensors in the throat of anything that has a reheat coil on it.
Yeah.
Because now you can control that temperature and hold it, because otherwise you don't know, you're guessing at that spot. But if you have a discharge air sensor, you can control it, watch it, and maintain that delta T, which will give you a better mix within the room, and your thermostat no longer becomes an altimeter, it becomes actually a temperature sensing device, because you're getting a better mix in the room. There have been lawsuits, and engineers have been cleaned up like you can't believe, because they don't know that one particular little phenomenon, because they keep putting more and more heat into it, and the room gets worse and worse.
Yeah. I agree with what you're saying. The greater the temperature difference between the two streams of air, the harder it is going to be to mix them. The problem with this situation ever working is it's like rolling a ball uphill.
It is.
You know, every time you roll it up, gravity wants to roll it right back, because it's sucking, the fan is pulling the air up, and you're trying to push the air down, and it's just going to want to come back up. So natural flow is going to be back up to the register, to the return grill. And if, like Mick was saying, if you have a great difference in temperature, you've about eliminated any possibility of it ever happening. If the closer they are in temperature, the better off you're going to be. But somewhere in the middle, you come down to a point where you get more velocity out of there. And when you have more velocity through that hot water coil, it's also cooler because we're not raising it as, we're not heating it as much. So, it's kind of a double benefit. We're about out of time here, but a couple things quick I wanted to touch on. If I tell this to Titus or whatever box manufacturer, what they're going to come back and they're going to say, oh no, not our boxes. We have a special pickup in the, here's my box here, in the inlet. They always have theirs in the inlet, which is usually about this far away from the damper. And then they go on to tell you in the instructions that we want 3 duct diameters in straight duct in front of that pitot tube. Because we need this, when I got my pitot tube here, I've got to get some straight air, like the nice picture that I gave you in the handout here. We can have nice laminar flow. That thing can read and give us a pretty accurate reading. If this air is swirling around, when it goes by there, that differential pressure is going to be whacked and it's not going to be accurate. So we've all seen this installation, right? Fronts come down, they got flex, usually about 13 foot of it. It's pinched off right there at the opening because the light was right there, so they had to cram it in there to make it work. And you've got no straight duct. Here's our pitot tube is right here. Here's our damper is right behind it. There's nothing straight about any air anywhere near there. So, if we can get a little bit of straight air before that box, you've got half a chance of getting a decent reading. Now, the box manufacturers will tell you that we don't use a pitot tube. We use a special amplifying, insert your trade name here. But when you open it up and look at it, all you see is this plastic thing. If I'm looking at a cross section here, here's one tube and here's another tube. They're back to back. One of them has holes on one side going downstream. The other one has holes going upstream. That's doing a, so if I'm looking down the duct, you got this thing here and there's a bunch of holes along there. And along the back side, you have the exact same thing. And instead of reading static or the pressure against the side of the duct, what they're reading is this downstream pressure. So you've got your air's flowing along here, it goes along here, and this kind of creates a little vortex, a little low pressure area. So instead of the normal static pressure, you get something a little bit less because you're getting a little vortex off of that. So they're not saying, well, with our box, they call it the K factor. Our K factor is not 4005 like you're using. Ours is something else. And so instead of needing 0.05 or instead of having 0.04 to get 300, they'll throw out things like ours is, 1.7 times greater than that. It's really amplifying the crap out of that signal. Well, do your math. What's 1.7 times 0.0465? It's still nothing. You double nothing and it's still nothing. So don't ever argue with a box salesman because he'll try and pull this on you, and it helps. it's probably better than nothing, but that's what it is. So crummy installation is going to be a problem for you. Troubleshooting, you're going to get up there and they're going to send you out and say, hey, this box isn't reading CFM. What's wrong with it? And you come up and you open the can, and you know it's hard to see what electrons are going through that airflow sensor. So you don't know what the heck to do. So you pull the tubes off, put your MagnaHelic on. You know, you got a nice 0 to 5 inch MagnaHelic. And the needle just barely quivers. Well, if all you got's minimum CFM, you got 0.0 something, that might be right. Try and get the box wide open so you get up to where you're reading something above 0.1. You know, and in my experience, you get much below, it'll read below 0.1, but you get much below there and it kind of trails off pretty fast. Some of those sensors will get down to a velocity pressure of like, I want to say it's 0.017, and that's like the minimum they'll read. So if you have a big box, that may calculate out to be, you know, 500 CFM on a 2000 CFM box. It may say, you know, it won't ever drop below, you know, that level, even with the damper completely closed, because of the resolution, you can't get down there. What the heck is that thing? Straight duct. You put, get the damper open, put your MagnaHelic on, so you have something to read. The other thing is, Andover uses a hot wire anemometer type of device for their airflow sensor. And what that is a orifice you've got your, you hook your plastic on here on each end, going off to the two tubes on your pitot here, and they have a tiny heater and a tiny temp sensor and a tiny temp sensor and an orifice in there, and they know the exact area of that orifice, and they know exactly how much heat that heater is putting out, and so they measure the difference in temperature and calculate how much air is passing over that heater. That is the way that thing works. So we actually have air flowing through that sensor, which means on the high side, we've got a filter to keep any of the lint and crud out of that orifice and out of that sensor, because otherwise you know what the inside of the ducts look like. They just fill up with dirt over the years. So you got to have that filter in there. And the other thing is by the book, those tubes can't be more than 18 inches long. If it's 1/4 inch, I believe it says 18 inches, and if it's longer than that, they want you to use 3/8. Because if you have too long of a distance, you're trying to send 0.05, through a little tube 10 feet away, you lose a lot in your lines. So keep those lines as absolutely short as you can. They've got to be absolutely tight because you can't afford to lose anything. There's a lot of these manufacturers that will come with the pitot coming off of them, and they'll have little plastic T's with a plug in the T, so that when the balancer comes along, he can take those plugs off and plug his meter in there and see what the differential is across it. I see those things crack or split or the little rubber stopper, the little rubber plug in the T, falls off or gets old and deteriorates and falls away, I just cut them out. I would just remove those suckers, get rid of them now. We have enough trouble with CFM. We don't need any help. Also, the pitot on the inlet are often made of plastic. If you have opportunity to see them before the ductile work goes on, doesn't hurt to look at them because sometimes they're cracked. And if that thing's cracked, then now we don't have the correct in or out pressure, and that's going to hose up your reading. The balancer will come along and put his hood on there with this big expensive differential pressure sensor reading his flow hood, and he'll tell you that that is absolutely, 657 CFM. And without changing any air whatsoever, he'll come back 5 minutes later and tell you it's 100 CFM different. And nothing has changed in the system. Everything's been locked down in between. So reading airflow is a pretty inexact science. Because of all the turbulence and all of these issues, it's tough to measure in the first place. So if you could get within 5% of real, you'd be doing fantastic. But I should probably let you go. Any last comments or questions? Anything? Brett?
How many filters do you ever change them?
Do they need it?
Yeah.
I'm never around on the tail end of that anymore. So, do they get?
Most of them don't know they're taking
No. Thanks, Lincoln, guys. Who's all down there, Darren?
Good work, good work.
There's nobody down there. Those are cardboard cutouts that they painted.
There's the people on this screen. A resolution on that.
Yeah.
Well, make good time.
I felt that, Jack. And here.
She was losing too.
Oh, sure. Yeah, because I got a problem too. Right now.
What's up, man?
Oh, yeah. Leg top, you turn fans, so what happens is,
Mark, you just parked in the parking lot down there, reaching the mechanical, where you guys got
all of a sudden, they equalize, they overcome, and I get a big building.
How's the temporary heat down there?
No, thank you. That helped a lot. It's always good.
Or they'll do all their silk door.
Yeah, they've done that for years. Don't leave the doors open down there.
Yeah, right.
Okay.